Hey guys, today's video is about naive Bayes. We've discussed the probabilistic classifier and basic probability theory in the last video, so we'll focus on naive Bayes today. To begin with, Bayes' theorem is the foundation of naive Bayes classifier. We'll quickly go through the formula, but don't worry, we won't go deep into how the formula is derived. The theorem goes like this. The probability of H conditioned on X is equal to the probability of X conditioned on H times the probability of H divided by the probability of X. It might look complex, but we'll go through it in detail now. To recap, the conditional probability of X on Y is the probability of X happening given Y has happened. And P of H and P of X is straightforward. It's just the probability of observing an individual event. Next thing we are going to discuss is the meaning of X and H. H stands for hypothesis, which is the target of classification, or to be more specific, it's the target attribute in the database. Then, X stands for evidence. Evidence is the observed tuples, or the facts, or the characteristics of a subject. For example, the model wants to predict whether a person will buy a car based on his or her age and gender. In this case, whether a person will buy a car is our hypothesis, and there are two possible outcomes, yes and no. Further, the age and gender are the evidence. Since we have two attributes here, X can be expanded to the vector x1 and x2. So, the idea is we predict whether a person will buy a car by comparing the probabilities of the outcomes conditioned on the evidence. It's normal if you still feel confused. We'll go through an example later. Now we move on to naive Bayes. As we said before, naive Bayes is based on Bayes' theorem, but it actually uses a simplified version of Bayes' theorem. In naive Bayes, probability of H conditioned on X is in proportion to the probability of X conditioned on H times the probability of H. In the original Bayes theorem, there is a probability of X in the denominator, but in naive Bayes, we ignore Px, since it's the same for all classes or hypotheses. For instance, if we want to predict whether a 22-year-old female will buy a computer, we need to calculate and compare these two probabilities through Bayes' theorem. However, the X, or the evidence, for these two probabilities is the same. X contains two characteristics, age and gender. Intuitively, probability of X is also the same since X is the same, so we can ignore Px in the denominator. Moreover, we'll use Ci to replace H from now on, because each hypothesis just represents a class in target attribute. Using Ci is more universal in naive Bayes. Alright, so now we have simplified Bayes' theorem. The thing is, we may have many evidence X, such as gender and age. How do we calculate the probability of all attributes conditioned on the class? In fact, naive Bayes assumes all classes are conditionally independent. In other words, we just multiply the conditional probabilities of all attributes, since the attributes are not correlated. As you can imagine, this assumption is naive. For example, a person's education level may be related to his or her credit level, but naive Bayes just assumes all attributes are independent. Surprisingly, although this assumption rarely happens in real life, the result of naive Bayes turns out to be fine most of the time, so it's still an important classifier. The last thing I want to talk about is the pros and cons of naive Bayes. The main advantage of naive Bayes is the speed. It's a fast classifier that we can put large amounts of data into the classifier and get the answer soon. In fact, the class independence assumption allows the naive Bayes to do the calculation much faster than the algorithms that do not have this assumption. However, because of this assumption, naive Bayes sometimes has low accuracy. Of course, it works fine most of the time, so it's a popular classifier, but this assumption is so naive that it sometimes deviates from the reality and makes naive Bayes have poor performance. So it's kind of like a trade-off. Independence assumption accelerates the naive Bayes, but sometimes lowers its accuracy. It's your responsibility to check whether the attributes are highly correlated and decide whether to use naive Bayes or not. Alright, that's the basic idea of naive Bayes. We'll go through an example in the next video. Thank you for watching my video and see you next time.